So I decided I'll start with the example 1 issue, the complexification. So here's definition. Given V over the reals, all right, so a real vector space, we define V sub C, the complexification of V as the complex vector space formed by V sub C equals to V cross V. But for the sake of where we'll use x comma y equal to x plus iy without danger of confusion in this construction. All right, but if this is confused, if you're like, well, you're assuming the point, fine, get rid of the I, work it all out with Cartesian products. It's kind of like that construction, the Gauss construction of the complex plane. It's the same thing. It's just you can do that for a vector space also. So, of course, we know how to add vectors in the Cartesian product. It's the usual component-wise addition. But the issue is, and we know how to real multiply these. Remember, these are vector spaces over the reals. But the issue is complex multiplication. How do you define that? So, if I use the you know, this notation just for the sake of humoring my detractors, that would be ax minus by, comma, you know, ay plus bx, right? But I much prefer to say, well, the complex multiplication is defined in the natural way, right? I mean, you see, I can't make up my mind which term comes first, but the point is you distribute, and you know, we have I squared equals to minus 1, right? Of course, I squared equals to minus 1 is implicit in this up here, right? If you take this to be the definition, which you can. All right. Notice that all of these things are well defined, because why? These are real numbers times vectors in V, where V is a real vector space. So these are all legit by the scalar multiplication that is given to us by assumption, the vector space over the reals. Okay, great. And so we've got addition, we've got complex scalar multiplication, and you can easily check the rest of the axioms, because it is, after all, just the direct product. I mean, it's the Cartesian product, it's the direct product space. So indeed, it is a complex vector space. This is the complexification. That's it. Okay. And if, it's like, here's a low-lying theorem. If beta equal to V1, V2, Vn is basis for V over R, and then beta is basis for V sub C over C. So what I'm saying is the dimension, the real dimension, right, of V of R is given to be n. Well, the complexification will have complex dimension n as well. which incidentally is going to mean that if we were to calculate the real dimension of the complexification, right, we wouldn't have n, well, I say implies this is equal to 2n. So, you know, also gamma equal to, let's say, you know, I mean, there's various ways of writing it. You could do like, we could do gamma 1 is like beta union with I times beta. Or gamma 2 equal to, this one's kind of more annoying, but it makes nicer formulas. V1, IV1, V2, IV2, dot, 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 Vn, IVN. If memory serves me correctly, that is the basis for the complexification, which makes our formulas nicest. But that is a real basis for the complexification, thought of as a 2n dimensional real vector space. We want to do that because our ultimate goal is to extract real data from the complexification to then take back to our real vector space and use to serve our purposes. Right? So this complexification is just a means to an end for us, because we complexify, then all of a sudden all of our polynomial equations have all the solutions we want, and hooray. All right.
Can we generalize this for any field instead of the reals, any field that is not algebraically closed?
Can you replace your, can you take, well, your question, the question is can you take a vector space over a given field and make it a vector space over an extension field of that given field? The answer is yes.
Like the idea of complexification generalized to?
Yes. Yeah, I mean, an algebraist will like poo-poo what I'm doing right now and say, oh, it's just the tensor product. It's just this, why must you do this? This is just this. So why must you do all this? I do all this so that it's concrete and understandable by students. But it is true, it really is up to isomorphism, the tensor product of C with V. And if you had a different extension field, you know, you could take the tensor product with that extension field. Of course, that's more interesting when you're not working over the reals and you're working over something like a finite field, which has, you know, blah, 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 blah. All right, okay, so. Whew, well, that happened. All right, so this is your complexified vector space. Now we're using this to study an endomorphism on a vector space, right? So if we have T from V to V, then I would say T sub C, which is going to be from V sub C to V sub C, is the complexification of T defined by, how do we define it? Well, simply like this. T sub C of x plus iy is equal to T of x plus I times T of y for all x and y in the vector space, right, over the reals. Or you could equally well say for all x plus iy in the complexification of V, that would be equivalent logically. So there it is. This is the complexification. So of course, if we're given a linear transformation, we can study the interplay between the characteristic polynomial. We can study the interplay between like Oh, okay, so this theorem right here, which we could, this wouldn't have been hard to prove, all right, I'm just being lazy. But you notice then that we can talk about the matrix of the complexification with respect to the beta basis, right? This is a complex n by n matrix. And so the characteristic polynomial of the complexification is a nth order polynomial in T over C, right? Therefore, by the fundamental theorem of algebra, there exist n complex eigenvalues for the complexification. I mean, there exist, I should just say it this way, there exist n eigenvalues in C for the complexification, possibly repeated, right? Possibly complex, of course. So, how do we make contact with the real world? Well, definition. Thank you. Definition. V x equal to, oh my bad, z equal to x plus iy in v sub c with y not equals to 0 is a complex eigenvector of T, which is a mapping from V to V with eigenvalue lambda equals to alpha plus I beta if T sub C of Z is equal to lambda Z. And I probably should have put this before the definition, but as we sort through these calculations, we're going to find that by necessity, beta must be non-zero here in this context, right? So this would not be an eigenvector of T. This is something new, all right? Now, in other words, to put it in words, a complex eigenvector of a linear transformation is simply an eigenvector of its complexification. That's it. And then one wonders, okay, so what does that tell you about the original transformation, right? Like, so let's work it out. Let's do the calculation, okay? So let's calculate. Consider lambda equals to alpha plus I beta and z equals to x plus iy, where, you know, alpha and beta are real numbers, x and y are real vectors, right? And beta and y are not equal to 0. Maybe I don't need to assume that. Maybe the calculation will show that to us in a minute. All right, like, let's find out. But such that T of z equals to lambda z, right? Now, my bad. Can I write T of z equal to lambda z? According to my current annoying, burdensome notation, right? I put a sub c on here. Now, when I teach other courses, I don't put the sub c on there I just use words, I say. We complexify the operator, and I just feed the operator a complex thing, and then, whatever. You're fine. What's that?
Math history book,
Ah.
1970. Translated from German in 1958.
Huh.
So,
Interesting.
interested in math history. I just put it there because somebody donated these books
Uh-huh.
to the math department,
Yeah.
and I already have that one on my shelf.
Wow, that's funny. Interesting. So, let's see here. So that, by definition, we've got, T sub c of x plus iy is equal to alpha plus I beta times x plus iy, right? But this, by definition of the complexification, is t of x plus I times t of y. And on the other side, we've got alpha x minus beta y plus I times the quantity beta x plus alpha y. Using my definition of the complexification and the complex multiplication of the complexified v there, both. Then what? Well, remember that this is just notation for Cartesian product, right? So the only way two pairs of vectors from v cross v can be equal is if their first and their second components are separately equal, right? So in other words, we can equate the real and imaginary components in the complexification. And that gives us t of x is equal to, well, alpha x minus beta y. And it also gives us that t of y is equal to, well, looks like beta x plus alpha y. Now I think if you sort through it, if we think about it, let's think about it for a second. Let's just think, not right. If I had y not equal to 0 and I tried to make this a real eigenvalue, then oh man, my bad. Maybe I should assume that. I should assume I have an eigenvalue. I think it's an assumption. I should look at my notes to be more careful, like, which came first, chicken or egg, horse before cart, all that kind of thing. But well, here's the thing: is if beta was 0, if beta was 0, I would have t of x equal to alpha x. I would have t of y equals to alpha y, right? Which would mean that alpha is a real eigenvalue of t, so that equation's not unreasonable to think about. But what I'm interested in is the case that we have a genuinely complex eigenvalue, right? The imaginary part's non-zero, and I want to ask, what is then the substance of a complex eigenvector with respect to such a genuinely complex eigenvalue? All right? And apparently, if you have we have this, right? So what this then means is that if I look at t restricted to, let me just call it w for lack of imagination, and I take, and look at the basis, I'll call it gamma. And I'm going to let gamma be x and y. What's the matrix of T look like then? so you can see the formula is right here, right? So t of x is this. So we'd take like alpha x minus beta y, gamma coordinate of that, then beta x plus alpha y, the gamma coordinate of that, which would be what? So x is the first thing in the basis. So I have, yeah, alpha minus beta,
Beta
alpha. Which is almost our usual matrix representation of a complex number, you know? But, okay, so like here's the theorem. If, you know, T is a mapping from V to V, and there exists lambda equals to alpha plus I beta, where beta is not equal to 0, is a complex eigenvalue of T, then the matrix of T restricted to W, where W is equal to the span of, you know, x comma y, and, you know, T of x plus iy is equal to alpha plus I beta times x plus iy, right? Gives, you know, matrix of T with respect to that basis. That basis is, like we just found, alpha minus beta, beta alpha. So one of the things I'm claiming, and I haven't proved yet, is that x and y have to be linearly independent as real vectors. So if we take, like, you know, c1x plus c2y, and we set it equal to 0, that should imply that c1 equals 0, c2 equals to 0, right? I think if I try to prove it directly, I get stumped. Let me look at my notes. I have a proof of this. It is true nonetheless, but, you know, why is it true? A second here, I'll tell you where it is. By the way, I violated the order of my notes. In my notes, I do the generalized eigenvectors first, and then I do the complexification second. So I've skipped ahead to section 8.3. I will go back to section 8.2 in a moment, but it's probably, I'm probably going to pay the price too, because I'm going to have to circle back to this section later after I've talked about the Jordan form, because then we'll have to talk about the complex Jordan form. Because what we're doing right now, we only know about eigenvectors, so we can only do the complex eigenvector thing, right? We can't talk about complex generalized eigenvectors, which is what we'd like to talk about eventually. Let's see here. So proposition 8.3.5 on page 238 proves my assertion that if you have a basis for the real vector space, then it's also a basis for the complexification. The proof is there in gory detail. And I also mentioned, like, the usual choice of basis is v1 comma iv1, v2 comma iv2, right? Excuse me. All right, let me get to it here.
It says page 238.
Yeah, page 238. Let's see here. So I think the itch I'm trying to scratch right now is addressed on page 242 in theorem 8.3.15. That's where I have a proof that if you have a complex eigenvector a plus ib, then a comma b is a real linearly independent subset of v. Oh yeah, I would definitely get stuck on it, because the proof involves another idea which we have not yet talked about. Ooh, 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 ooh. This is something I should talk about, though. What's the other thing we do with complex numbers? We do what? We multiply complex numbers, but the other thing we do is what? We add them. Yeah, well, we've been doing that. But the other thing we do is we take the complex conjugate, right? So complex conjugation on the complexification is defined by the obvious rule, right? So like x plus iy conjugate is x minus iy. Okay, so that's how we define complex conjugate on the complexification. Check this out. So if I have t sub c, right, of x plus iy equal to alpha plus I beta times x plus iy, right? Then that implies, of course, that the, let me write it more simply. Oh, good grief. Fine, I just have to write it out. T of x plus I t of y is equal to alpha minus alpha x minus beta y plus I times alpha y plus beta x, right? But then, that was, we talked, I mean, that's the same equation I have up there. Complex conjugate this, though, what do you get? So you get t of x minus I t of y is equal to alpha x minus beta y minus I times alpha y plus beta x. Just, and how do I know that's the complex conjugate? Because remember, t of x and t of y are real vectors by assumption. T is a real endomorphism. So this, if you tilt your head and squint, you can see is actually alpha minus I beta times x minus iy. And on the other side, we have t of x minus iy. And to be clear, of course, that's actually the complexification, right? So in other words, theorem t of v, t sub c equals to lambda v implies that t sub c of v conjugate is equal to lambda conjugate v conjugate. So complex eigenvectors of the complexification of a real transformation, they always come in conjugate pairs. And then And then, since lambda and lambda bar are distinct, they're distinct if beta is non-zero, right? If beta is non-zero, then lambda and lambda conjugate are distinct eigenvalues. So by the theorem that distinct eigenvectors, eigenvalues with distinct eigenvalues, eigenvectors with distinct eigenvalues are linearly independent, we then have that v and v conjugate are linearly independent. Right, so this implies that v and v conjugate are linearly independent over the complex numbers, right? But if you know that, what does that tell you? Well, notice that stupid cough. So, you know, we've got x plus iy times, you know, a plus ib plus a1 plus ib1, a2 plus ib2 of x minus iy equals to 0 implies, you know, a1 plus ib1 equals to a2 plus ib2 equals to 0. I mean, that's what we have. And I think we can use that to prove linear independence of x and y. Like, what is x, what is y? Like, x is equal to 1/2 of v plus v conjugate, and y is equal to like 1/2i of v minus v conjugate. So if you look at that, right, if you look at that, if you have c1x1 plus c2x2, what do you got? I mean, c2y, I'm a dummy. Well, in view of these equations right here, you've got what? You got, you know, c1 over 2 plus c2 over 2i v plus c2 over 2i minus c1 over 2, I think, v bar equal to 0, right? But then what? Well, by the complex linear independence, we have that the complex linear combinations of C1 and C2 as pictured in that equation are separately 0. But that then implies that, you know, through just simple 2 equations and 2 unknowns, see that? Like, so we have now a linear combination of this type. So we can see that this must be equal to 0 and that must be equal to 0. But you can solve those 2 equations and 2 unknowns to get that C1 equals to C2 equals to 0. All right, enough. I think I've done enough. I mean, anyway, the point is, if we have a complex eigenvector, we can take the real part and the imaginary part of the complex eigenvector and use it to form a basis for which the linear transformation restricted to that part of the basis has a matrix which is just one of these guys. And what is this? This is a rotation dilation block. See, because what I'm going to erase this. I don't think we need this anymore. So, see, if we look at alpha, beta, minus beta alpha, we can rewrite that as 1 over alpha squared plus beta squared, right? Well, excuse me. The square root of alpha squared plus beta squared alpha over square root, beta over minus beta alpha. All right. And I believe that's you can see that this is actually of the form. See, what's bugging me, Ernesto, is I feel like I might be missing a plus or minus here somehow, and I can't see where I'm missing it from. But just a little bit uneasy about maybe I've missed a sign in here somehow. Because it seems to me what I'm about to say is that it's really a rotation times the dilation. I don't even see, at the moment, I don't see the possibility for a minus. So it could be an inversion. Oh, maybe it's just that, well, I don't know. I don't know. Are we good? So, this is the first example of the real Jordan form. This is the real Jordan form 2x2 block for lambda equals to alpha plus I beta. And the cool thing is, if you find the complex eigenvector, you're done. You don't need the conjugate. Why? Because the conjugate eigenvector, it's got x minus iy. It's the same base. You already got that basis. And so one complex eigenvector gives you two real vectors. So, all right? Yeah, that's it. Come on. All right, so we will come back to this again after we've talked about the generalized eigenvectors for a bit, okay? So let's turn over to generalized eigenvectors. What are those, and what do those do for us? Now, I will admit to you, I'm not going to actually give you a complete calculational template on how to calculate these. It's true, I don't. My current set of notes, I think they're a little bit lacking in that regard. I don't have a complete algorithm on how to calculate a Jordan basis. It's a little bit subtle, but it basically amounts to you have to find the generalized eigenvectors first and then go from there. My usual approach is to find the eigenvectors first and then to kind of bootstrap up. That is okay for many, many examples, but there exist examples where if you start with eigenvectors and you try to build your way to the generalized eigenvectors, things get kind of tangled up. Best way I can explain it. Now, my brother taught linear algebra for years until finally one year he stumbled upon the example with the tangled, and it was like in an honors class at Rutgers, I think, and then he was like, oh, snap. So, but anyway, because we'd always just find the eigenvectors first, right? So anyway, definition. V is, let me say X rather. X is generalized eigenvector of order P with lambda eigenvalue for T if T minus lambda to the power P acting on X is equal to 0, but T minus lambda to the p minus 1 acting on x is not equal to 0. So a generalized eigenvector of order 1 is just an eigenvector. So, but typically we don't just do this. We have a theorem, which is that if there exist, let's say, x1, x2, dot, 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 xk not equal to 0, for which t minus lambda acting on x sub I is equal to x sub I plus 1, then make sure I got the numbering right here. I'm sorry. I got to think about this for a second. I think I want the other way around. Minus 1. All right. Then x sub j is a generalized eigenvector of order j with eigenvalue lambda for j equals to 1, 2, dot, 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 k. And we refer to such a collection of vectors as a chain, a k-chain of generalized eigenvectors with eigenvalue lambda. Let's see how that chain condition, so this is the chain condition right here. This right here is the chain condition. All right? That's the secret ingredient right there. So notice that t minus lambda x1 is equal to 0. By the way, set x minus 1 equals to 0 for notational convenience. That needs to be assumed. Okay. Oh man, I'm sorry. Oh. All right. So that, of course, makes it a eigenvalue, which makes it a generalized eigenvector with eigenvalue 1. Consider t minus lambda squared acting on x2. Well, that's t minus lambda acting on t minus lambda of x2. That's the definition of squaring an operator. It's function composition, right? But this, by assumption of the chain condition, is x1, which is 0. So we have that, we have that t minus lambda on x2 is equal to x1, which is not equal to 0, yet the square sends it to 0. Therefore, x2 is generalized eigenvector of order 2.
And this is for OI.
Yep. Yeah, this has to hold for I equals to 1 to da 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 k. That's assumed, yep. I suppose we could prove this by induction, right? So like inductively assume inductively suppose t minus lambda to the, like, you know, j of x sub j is equal to 0, yet t minus lambda sub j minus 1 of x sub j is not equal to 0, right? So then consider what? If we consider j plus 1, acting on xj plus 1, then what do we get? Well, t minus lambda acting on t minus lambda to the j power, right? Acting on xj plus 1. Oh, rats. All right, I see I need to peel out. I chose poorly, Ernesto. I chose poorly. I should have put the j. See, I should have put the j over here. If I did that, we'd be in a better condition, because now I know I can apply the chain condition, and I get that this is what? This is x sub j, right? But then, by the induction hypothesis, that is equal to 0, right? And what else do we need to prove? We also need to see that t minus lambda to the j on xj plus 1 is not equal to 0, right? So it's almost the same calculation, right? So like that's t minus j to the j minus 1, t minus, not j, lambda, t minus lambda acting on xj plus 1, but then apply the chain condition, and we've got t minus lambda to the j minus 1 acting on xj, right? But then by the induction hypothesis, that's assumed to be non-zero, woohoo! Now I don't usually do this induction. I usually just calculate it for 2, and then I calculate it for 3, and then I go, come on, you know? Because it's obvious that the chain condition works. So how do I find generalized eigenvectors? I solve the chain conditions. That's what I do. I just solve the chain equations to look for them. So like for the example 2 we had earlier today, I think I can erase this here without loss of much. So here we'd be looking for like A minus 2 times the identity matrix times u vector equals to the eigenvector. What was the eigenvector with eigenvalue 2? It was just E2, right? That would be the chain condition for a generalized eigenvector of order 2 with eigenvalue 2 as it happens for this one. And so that specifically would give you the equation minus 1, 0, 0, 0, 0, 1, 0, 0, 0 times the vector I don't know equal to 0, 1, 0. So see that middle equation forces w equals to 1. And it leaves that equation's trivial, that equation's trivial. It leaves the other two free. So like in principle, you can use u equal to anything here, 1v. But you don't really want to do that, because if you think back to our earlier discussion, we'd already used really? I'm a dummy. W equals 1. Is that what this looks like? No. Stupid. Me, not you. 1 is the W. Duh. So what did we find? We found E1 and E2 were eigenvectors. So this, I would, for just reducing clutter, I would say let U equal to V equals to 0. Because otherwise I'm just adding like a copy of the eigenvectors I already have into my generalized eigenvector. It's just nicer to have it E3. So what this then means is that for this matrix, E2, comma E3 is a 2-chain for A with eigenvalue lambda equal to 2. My example 2. And of course, if you take E1, E2, and E3 together, you have a basis, right? It's time for me to confess something. When the standard basis is a Jordan basis for your matrix is already in Jordan form. This is the Jordan form of a matrix. That's the next best thing to diagonal, is we have the eigenvalues down the diagonal, and then we have some ones on the superdiagonal as needed to reflect the presence of generalized eigenvectors. The ones on the superdiagonal, they reflect the possibility of needing chains of generalized eigenvectors to complete the basis. So do you have a class at 12? Okay. Let me finish this thought here. So the way you use generalized eigenvectors to calculate the other solution here, it's kind of sneaky. I need about 20 minutes to explain that. I won't do that right now. But let me just tell you the theorem. The theorem is this. You can always find a generalized eigenbasis for a transformation. Let me say this again. So theorem, if all lambda 1, lambda 2, lambda s are elements of your field. In other words, if you have a characteristic polynomial, all right, such that the zeros of the characteristic polynomial are all in your field, then I don't mean I don't mean these are all zeros. I mean they're all of the zeros of the characteristic polynomial of t. All right. Then V is actually the direct sum of k lambda 1, k lambda 2, k lambda s, where these are generalized eigenspaces. And in particular, like k lambda j, what it's going to be is it's going to be the span of all lambda j chains for t. So basically, you find all of the generalized eigenvector chains, and you string them together. That defines the generalized eigenspace for eigenvalue lambda j. There's a better way of defining it in terms of annihilating a power of the transformation minus the eigenvalue. That's exactly the part of the theory which my notes are weak on. But anyway, so finally, let me just talk about what's the matrix. If we let beta, right, be a k-chain, so let's suppose beta is x1, x2, xk, right? What happens if you look at the matrix of t with it? Suppose that the whole, just for the sake of convenience, let's suppose that That's a basis for your whole space, just for the, otherwise we'd be talking about the restriction, we'd be talking about the restriction of linear transformation to subspace, but I don't want to do that. Then T beta beta, it would be, well, golly, T of x1, right? T of x2, da da da, T of xk, right? Now, what's the formulas for these? Well, let's look at this chain condition up here. Let's look at the chain condition, and let's rewrite it. Let's repackage this. What this is really saying is that T of xi, right, is equal to lambda I xi plus x sub I minus 1. So what we're looking at here is lambda x1, and then lambda x2 plus x1, and so forth and so on, all the way down the line until we've got lambda xk plus xk minus 1. All right? What does that matrix look like? Well, that matrix, this gives you lambda in the top spot. Like x1's the first thing in the basis, right? So this makes my first column just lambda with zeros underneath it. See that? This one, does that make sense? Like x1 is the first thing in the basis. This one puts a lambda in the second spot, and it puts a 1 in the first spot. So we get 1 lambda. And the next thing you're going to get is 0, 1 lambda. All right? And that continues. All the way down to the last one, which has got a 1 on its superdiagonal like that. So this, by definition, is what I call the kth Jordan block of lambda. And we can prove, I'll explain next time we meet, that if you choose, if you can construct, all right, if you can construct a basis for your transformation which is formed by a union of k-chains, then the span of the k-chains, they give you independent subspaces. And if you use the k-chains as to form a basis, and you can do this, then the restriction of the transformation to the k-chains, they're all just Jordan blocks. Of course, this falls apart when your eigenvalues aren't all in the field. So in the case of the reals, you just complexify, you find the complex Jordan form, and then it turns out that instead of having this, you've got like alpha minus beta, beta alpha kind of blocks paired with some like 1s on the super. It's a little bit complicated what happens in the complex case, but I mean, in the real Jordan form, it's a little bit more subtle. But yeah. And so the deeper thing here is that any matrix is similar to its Jordan form. So if you want to prove general things about arbitrary matrices, if you can prove it for an arbitrary Jordan form, you've proved it for an arbitrary matrix if the question that you're looking at is a question that is playing well with similarity of matrices, as often it is. So it's an incredibly useful tool. We should teach it in undergraduate linear algebra without fail, but we just don't. So anyway, I will shut up.